Nice to see you. So last time we introduced Gauss law, and who will remind me what is that about? So what it relates to each other. We have flux of electric field. We consider such flux of electric field through a closed surface, which in other words can be also called Gauss surface, that closed surface which we pick up for application of Gauss law. So we can represent it in general form as integral over closed surface of dot product electric field vector and dA vector, which is dA vector is small area of the small segment of this closed surface, its area, and multiply to unit vector of its to its surface, like unit normal vector to its surface. And Gauss law tells us that this should be equal to electric charge inside this closed surface divided by epsilon naught, which is universal constant permittivity of free space. So some comments on this to make it clear. This charge is only that charge which is enclosed inside the surface. And keep in mind there could be other charges outside the closed surface. However, they are not taken into account here. But when we are considering this electric field vector, then we need to take into account electric field created by each charge inside and outside of the closed surface at each point of this closed of the surface of the Gaussian surface in order to determine the net electric field vector and run this calculation, the integral over closed surface. So when we deal with electric field, we need to take into account contribution of all charges around the surface and inside the surface. However, here we have shown during our derivation last time that no matter how many charges we have outside, they will not contribute to net flux of electric field through a closed surface. Only those will contribute which are inside. So that is the main message which we need to remember from Gauss law. And next step, we need to learn how to apply this. So I shortly mentioned last time that it is very convenient for some cases to apply Gauss law in order to determine electric field vector created by continuum of electric charges. However, that works in certain conditions, specifically when this continuum, like this distribution of electric charges, possesses certain symmetry, either cylindrical or spherical symmetry. So then it becomes really easy for application of Gauss law. There are several rules which will define how we pick up the Gauss surface, this closed surface, in order to apply Gauss law to determine electric field. So first, we need to be sure that at least like one of these rules is applied to all segments of the closed surface. So let us consider these three rules. Like first, we need to be sure that at least for one of these segments, we have electric field vector as constant. it doesn't change with position. So that is important because we need to um, determine its magnitude, and if it's changing from point A to B, then it will be difficult. So we need to align. So we have some distribution of electric charges, like some continuum of electric charges, and then we need to thoughtfully decide what kind of closed surface will fit perfectly into these conditions in order to allow us to determine electric field vector from direct application of Gauss law. So first rule, we want to find surface element, like part of this closed surface where electric field is constant. So second, um, we should find such segments of this closed surface when electric field vector is either perpendicular to the dA vector, means to the normal vector of the surface, or parallel. So both are working well because we either have just product of magnitudes of two vectors, or it will be equal to zero because when electric field vector is parallel, well, perpendicular to the normal vector to the surface, there is no flux of electric field. It's equal to zero. So, and one more, it also convenient if it's possible to find such a surface, like element of the closed surface, where electric field is equal to zero. So there is no electric field, and obviously it makes our life easier. So we can consider that there is no electric field. So let us consider several examples how we can apply Gauss law in order to determine electric field vector created by a continuum of electric charges. So let's do first a consider some linear distribution of electric charge along a wire. So let's say this is our wire, which carries some positive charge with the linear density lambda. So that is uniform linear distribution of positive charge along this wire. Since we have this symmetry here, so we will have like radial symmetry of electric field vectors going from the wire in all directions around the wire. And let's say we want to determine magnitude of electric field vector created by such a wire. We consider that this wire is infinite long, so the length of the wire is not limited. And we are interested in some point of space at the distance r from the wire. So here in this point, let's call it point P, we want to know what will be the electric field vector. So what we can do, we did something similar previously. We can divide this in small segments, calculate electric field created by this kind of point charge small segment of the wire. At this point P, do this for each part of the wire, calculate the net electric field by summing up all vectors of electric field created by each of these small segments. And eventually, when we put them all together, we will get the resultant net electric field vector in this point. However, we can skip all these steps if we apply Gauss law. So how would it look? In this case, we should use some cylindrical closed surface, taking into account the symmetry of electric field and charge distribution. So it will look like this. We have the wire, then we have cylinder closed surface, with radius r. So that is the distance at which we want to determine electric field vector. So let us consider some length of this cylinder, L, and what we have now. So we do not consider, let's call it surface 1, and here we have surface 2. We do not consider these surfaces 1 and 2, means the sides of the cylinder, like ends of the cylinder, because in this case electric field vector is perpendicular to dA1 and dA2 vectors. And since it's perpendicular, it just goes in this direction. So this is electric field vector. It will not create any flux through these surfaces. So that's why we should consider only surface 3, which is the side surface of the cylinder. And here we can consider just small element of its surface. This is dA vector, yes. When we consider this vector, let's say we have a cylinder. So this is the normal N1, normal unit vector to this surface 1. Here is surface 2, and this is N2 unit vector. And here we have N3 unit vector. We know that electric field vector goes like perpendicular to the wire in all radial directions. So if we place this wire here in the center of the cylinder, then electric field will be aligned in this direction and normal unit vector in this direction. So, and the direction of this vector A1 vector is just area of the surface element multiplied by unit normal vector. So direction will be the same. So this vector A1 vector will go up and electric field vector will go at the right angle to it. That's why they are perpendicular. And in this case, the electric field flux through this surface element will be equal to 0. And when we consider this surface 3, like the side surface of the cylinder, here we will have also electric field vector, which is parallel in this case to dA vector, and that's why we can do the calculations, because there is electric field flux. So the total electric field flux through this cylinder, closed cylinder, will be defined as follows. So it will be integral of E vector times dA, let's call it 3 vector. So what is important here, that electric field is uniform in every point of this side surface, because we have uniform distribution of linear distribution of electric charge, means at every point of this side surface, electric field will be the same. That takes into account the symmetry of this case. And that's why we can take out from the integral electric field. So we will have E times integral dA3. I skip here on the vectors because they are parallel to each other, so there is just cosine of angle 0 will give us unity. So we don't need to consider vectors anymore, only absolute values. So now we have constant electric field, which we yet don't know, and that's our goal. We want to know what will be the electric field in this point at the distance r, point P next to the charged wire. What will be this part? Who will tell me? So it's area, side area of the cylinder, and that will be 2 pi times r times L, the height of the cylinder. And now we recall Gauss' law. So what it tells us, so we have it here, that the flux through a closed surface should be equal to electric charge enclosed in this closed surface divided by epsilon naught. Q internal divided by epsilon naught. So now tell me what will be this Q internal in this particular case. So we have the flow formed by the cylinder. Yes? Lambda by L. Lambda times L. So the linear distribution by density of electric charge means coulomb per meter of this wire. And here is the length of the cylinder. So if we multiply these two parameters, we get the charge, the total charge enclosed in this surface. So this will be lambda times L divided by epsilon naught. So let us substitute this here and write it again. So it will be electric field times, so this is the side area of the cylinder, 2 pi times RL, and that is equal to lambda times L divided by epsilon naught. So now we can cancel out the length and rearrange it in order to solve for electric field. So that will be electric field magnitude will be lambda divided by 2 pi epsilon naught times r. And that also can be represented in terms of the electric constant, 2 times Ke times lambda over r. So we see that electric field reversely proportional to the distance from the wire, and now at any distance of this infinitely long wire, we can determine magnitude of electric field. So another example which we should also consider. Yes, sure.
So it doesn't matter how long the wire is.
So actually, as you see here, we cancel out length. So it's actually not about wire length. It's about the segment of the wire which we consider, because that's the length of the cylinder. not of the wire. Wire is infinitely long. And yes, actually, it doesn't matter when we consider length of the wire much larger than the distance from the wire to the point where we want to determine electric field, then it doesn't matter. And this is the equation for electric field created by such charged wire. If the wire length is comparable to the distance, then you need to do this integration and calculate as we did previously.
What they've done in winter projects,
Yes?
such will be given as a concept or use some algorithms.
Well, usually it depends if what is given, either linear charge density, or for instance, it could be statement that electric field at some distance to this wire is given, then you need to calculate the linear charge density. So depends on the conditions. But now you know how they are related to each other and why. So let us consider one more example, and that will be kind of also important example. We will use it in the future when we work with parallel plate capacitors also, and some other examples. So let us consider a plate with surface density of electric charge sigma. So let's say it's some positive electric charge distributed over a very large plane. So we consider it's just infinitely large. Bless you. So now the question will be, what will be the electric field next to this surface? And how we approach it? We can again draw here a cylinder. So it will be our closed surface, Gauss surface cylinder. It goes through and ends somewhere here. So we kind of divide cylinder in two halves with this plane. And again, we have several surfaces. We have surface, let's say 1, 2, and 3. So according to the symmetry of the case, we have electric field vector perpendicularly oriented towards the plane of this charge, towards the charged surface. So this is our electric field vector. And keep in mind that it also goes in other direction from the other side of the plane. So we have now the case when there is no flux through which segment of this cylinder. When the side surfaces of the cylinder are parallel to the charged plane. So in this case, we do not have flux of electric field vector through the side surface, through the surface number 3. So then we may just ignore it. So again, we align it in a proper way, because if it's aligned in a different way, that would be more difficult. But now we have two parts of the closed surface, part 1 and 2, when electric field vector is parallel to the normal unit vector, and for surface segment 3, normal unit vector is perpendicular to the electric field vector. So in this case, we kind of satisfy these conditions which are set for selection of Gauss surface. So now we need to get the flux of electric field. through this closed surface, and that will be 2 times E times A. So we consider that A1 is equal to A2 and is equal to some surface A. 2 because we have like two ends of this cylinder. And we also know, according to the Gauss law, that this flux should be equal to internal charge divided by epsilon naught. So now, what will be the internal charge in this case? So we have uniform surface uh, density, surface multiplied by area, and this area will be the same as the area of the base of the cylinder, because it doesn't change. So here will be sigma times area divided by epsilon naught. And we see that here A area is cancelled out, and we can get the equation for electric field next to infinitely large charge plate, which is equal to sigma surface density of electric charge distributed on this plate divided by 2 epsilon naught. So that is the example how we can apply Gauss law in order to determine electric field next to some continuum of electric charges. Of course, we need to take into account symmetry of these cases of electric charge distribution and pick up proper closed surfaces in order to make this task of finding electric field magnitude as easy as possible. Yes?
Sigma and alpha notation as in the first example.
Sigma notation instead of lambda notation? Oh, because they are different quantities. So lambda is linear distribution, coulomb per meter, and sigma is surface density. So it's coulomb per square meter. So meter in second power.
Since we had a surface there, so that's why we still, yeah.
Since we have this plane, so initially, like before we had the wire, there what we consider that's only the length of the wire. That's the only parameter what we need. But here we have a plane, so we need to operate with its surface, with its area. And area is given in square meters. So we have coulomb per square meter. Okay, so now our next step, once we already know application of Gauss law, is short consideration of conductors under electrostatic equilibrium. So remind me, what do we call conductors? What is the difference between conductors and insulators? Okay, what it means in more details. Electrons. So conductors, not necessarily only electrons, it could be some electrolytes with ions, for instance, but in general, we consider like metal as a conductor. So in that case, yes, we have electrons, but electrons, so negatively charged particles, which are capable of like, moving within the bulk of the conductor. So if we apply some external electric field, we put conductor out from the electrostatic equilibrium condition, then there is some flux of electrons, and that is electric current. So these materials are capable of conducting electric current, so they are called conductors. So if you have a conductor with plenty of these mobile negative charges within its bulk, but it stays in electrostatic equilibrium. So we don't create any electric charges. So there are certain conditions which are fulfilled for such systems. So first, we make a statement that electric field, even if this conductor is charged, or even if it's inside some external electric field, but stays in electrostatic equilibrium, there is no electric charge in the conductor. The electric field vector inside the volume of this conductor is equal to zero. So there is no electric field inside the conductor. So that's the first. We will consider them step by step in more details a bit just after defining them. So uh, the charge which we place on the conductor under electrostatic equilibrium will be redistributed only on the surface of the conductor. It will not go inside. So all electric charges which are placed on the electric conductor under electrostatic equilibrium will be only on its surface. So also we need to mention that the electric field which is created by these charges placed on the surface of a conductor in electrostatic equilibrium will create its orientation, the electric field vector created by these surface charges, will be always perpendicular to the surface of the conductor. So at any point, doesn't matter what shape of the uh, conductor, so it could be arbitrary shape conductor, if it is under electrostatic equilibrium, then electric field is always perpendicular to any small element of its surface. And also, if we consider electric charge distribution like surface density, because we mentioned that there is only distribution of electric charge, if we place some electric charge on a conductor, it will be residing only on its surface, and its density will be maximum at point with minimum curvature, with like minimum radius curvature. So where the highest curvature of the surface of this conductor, so let's say there is some spike, there will be the area with the highest density of electric charge placed on this conductor under electrostatic equilibrium. So let us consider several cases and explain why this is happening. So let's say first one, that electric field vector is equal to zero inside the conductor under electrostatic equilibrium. So if we place a conductor, let's say some piece of metal, inside external electric field, any suggestions what will happen in terms of charges inside this conductor? So how we represent the model of a metal in terms of charges? So that will be some periodic lattice, crystalline lattice, with positively charged atoms of this metal, so it's actually ions, and this net electric charge of positively charged ions will be compensated by mobile negatively charged electrons. So these are ions, positively charged, these are electrons. They are like some cloud of electrons moving around these positively charged ions. So in total, it's electroneutral system because they compensate each other. So now imagine that we place such a piece of metal in external electric field, and recall that if we place some charges in external electric field, there is some electric force which acts on these charges. So what will happen here? Will these ions move somewhere, like positively charged ions? They will not move anywhere because they represent the crystalline structure. They are fixed in their position, so they cannot move. However, electrons are mobile and they can be pushed towards one of the side of this conductor. So we will have kind of more electrons than necessary at the left side and more like positive charges uncompensated in the right side. So in this case, they will create internal kind of uh, electric field which compensate external electric field. And the net electric field inside the system under electrostatic equilibrium, when there is no electric current flowing through this conductor, will be equal to zero. So that is the reason why we don't have electric field inside. So now let us come to another point where we made a statement that electric charges, if we place some electric charges on a conductor under electrostatic equilibrium, they will reside only on its surface. So let us assume we have some arbitrary shape, three-dimensional, like bulky conductor. And then what we do here, we consider some closed surface inside this conductor. So that is our Gaussian surface inside the conductor, which is placed like very close to the right to the surface, but a little bit like from the inside side of the conductor. So now, what will be the electric field flux through such closed Gaussian surface? Assume that we have some charges like here in which are residing on the surface of the conductor. So we need to recall that, like, first condition which we mentioned, that electric field vector inside the conductor under electrostatic equilibrium will be equal to zero. So we have just shown this. So at each point here of this Gaussian surface, electric field will be equal to zero because it is located inside the conductor under electrostatic equilibrium. So that means that the flux of electric field through this closed surface will be also equal to zero. And that means, according to Gauss' law, that in this volume defined by the Gauss surface, and actually the internal volume of the conductor under electrostatic equilibrium, there is no internal electric charge. Because if electric field flux is equal to zero, then there is no charge enclosed in the Gauss closed surface. So that means that no matter what we put in terms of electric charge on this conductor under electrostatic equilibrium, all these charges will be residing only exclusively on its surface. They will not go inside the conductor. And now what we also can determine, that is magnitude of electric field vector next to the surface of this conductor under electrostatic equilibrium. So if we consider again some conductor, with, let's say, positive charge distributed all over the surface. Then we remember there was a statement I mentioned at the beginning that at every small segment of the surface of this conductor, electric field vector is perpendicular to the surface. So what we do here, we draw such a Gauss closed surface in the form of cylinder. Yes. So one half is outside the conductor and another half is inside. So this is the surface element of the conductor. So now within this small area dA, we have some uniform surface density of electric charge distribution on this conductor. Oh, and that is defined with sigma. So now we know that here is our dA1, let's say. So this is surface 1, this is surface 2, and this is surface 3. And here is the orientation of electric field vector. So what will be flux of electric field vector through surface 3? That will be equal to 0 because of orientation, perpendicular orientation between normal unit vector and electric field vector. Then what will be electric field flux through surface 2, which is here inside the conductor? 0, because electric field inside the conductor is equal to 0. So that is also 0. So we state the total flux through this closed surface will be defined only by flux of electric field through surface 1. So we can write that the total flux of electric field will be equal to the product of electric field magnitude and area of this side of the cylinder. So let's call it just A. So let's assume that A1 is A2 and this is equal to A. So here we consider only one side of the cylinder. So we have product of electric field magnitude and area of this side of the cylinder. We don't need vectors because they are parallel. And that, according to Gauss' law, is Q internal divided by epsilon naught. We already know that in this case we have internal electric charge defined as sigma times area. So surface density of electric charge distribution times area divided by epsilon naught. Here we compensate, cancel out area and electric field next to this close to the surface of an electrical conductor in electrostatic equilibrium is defined as sigma divided by epsilon naught. So it's similar to charged plane, but if you remember, we had this vector of 2 here in the denominator for surface, uh, charged surface. But when we are considering the bulk conductor under equilibrium conditions, we don't have any electric flux through the second surface. Yes?
I don't have electric flux at the same surface.
Through this part. Because we have shown earlier that electric field inside
It's
is 0. And if electric field is 0, then there cannot be any
but it's
flux.
flux too. second.
Yes. So second.
Ah,
So third surface because of orientation. So you see that here dA, like I forgot vector here, dA vector is parallel to E vector, and for third element of the closed surface, this dA3 vector will be perpendicular, and then we have dot product. We deal with the dot product. We have electric vector times magnitude times area, like d a3 vector magnitude, and times cosine of the angle between them. So it will be 90 degrees. It will be equal to 0, and that's why it is also equal to 0. Okay, so let us summarize our discussion for today. We uh, used previously derived Gauss law in order to determine electric field of distribution of electric charges and continuum of electric charges, taking into account their symmetry and picking up correct orientation of the Gauss surface in order to make us uh, this task convenient for calculations. We have shown how we can now determine electric field magnitude next to a continuous linear distribution of charges along a wire or along a infinitely large surface. So we also discussed the behavior of electric charges and electric field created by electrically charged conductors under electrostatic equilibrium. So taking into account the features of conductors materials properties, we have shown that electric field inside conductors under electrostatic equilibrium is equal to 0. It's compensated if even we place it in external electric field. Then we have shown that there is not there is no possibility for electric charges to be placed inside the, the conductor under electrostatic equilibrium, so they only reside any charges reside only on the surface of conductors. And we also applied the Gauss law and previous statements in order to determine magnitude of electric field at the surface of electrically charged conductor under electrostatic equilibrium. So we will continue on Friday with the introduction of electrostatic potential and everything what is related to this concept. Thank you for your attention and see you on Friday.